questions, we'll try to unpack some of the things he talked about in a very general way. So we'll go into some depth and talk about supervised learning, and later we'll continue with unsupervised learning and evaluation and optimization. For supervised learning, let's just start with some motivating examples. So Taman already mentioned some examples, and here are some more very simple ones, right? Like if you wanted to predict weight from age and height, how do you build a model? And how do you use that to predict weight for a new person if you knew their gender, if you knew their height, and if you knew their age? Or, you see all this past data, historical data, the stock price of Google, of Yahoo, of Microsoft from yesterday, from the day before. And if you wanted to know, if you want to invest, then you want to know if your stock price is going to increase or decrease. So how do you figure that out? How do you predict the stock price of Google stock for tomorrow if you've seen all the historical data from day before until even a month ago? And then there is an interesting example in robotic vision. If you have camera, or if you know what a robot saw previously in the past, where it went, what it's going to do, can you then start predicting the intensity of the image for now and in the future where it will be going? So here you know what it was seeing, what it saw in the past, and somehow you have to predict its path because you want to know what the robot is going to see and from there where it's going to go in the future. So how are we going to do these things? Do you guys have other examples of this prediction problem, supervised learning? So there are a few components here, right? You want to predict weight. And for this, you need to know the weight in the past, or you need to know weight from some example set where you also know gender, height, and age. And then you're using that, some new person's gender, height, and age to predict their weight. So you need to know a group of people, or you need to already know weight for some group of people to build a prediction model. And it's also the same with the stock price. You have seen stock price in the past, and you're now trying to predict in the future. So you already have some data to learn, and then you're using new data to predict similar outcomes in the past. So do you see a common ingredient where you already have seen some of the outcomes, and you're using that outcome to learn the model and then to also predict? So what could be other examples of supervised learning? Something you've used? Like if you run regression model, then you have used supervised learning, right? So object recognition, can you just?
You could have seen objects could occur anywhere in the image.
Mm-hmm.
You would have only seen training data where objects occur at particular positions in the image, but you expect your model to perform well in a novel image where the same objects occur there.
So your outcome here is?
Label the object and the position where it is in the image.
Okay, so the position in the image, and then you're learning position using other image in the new image, right?
Yeah.
There are some other examples?
So the advertisements that you see.
Yeah, so advertisement too, you want to know how well it's doing. Like if you want to put your advertisement in a website, you train using some data, and then?
You get the history of the person, like the browsing history.
Yeah.
Cookies, etc., and then try to predict if somebody will click an ad or not, and show them the ad that they are most likely to.
So the outcome could be clicking data. So in the history, like if how often it was seen, and using that, now you're gonna put it such that you get more clicks, right? So you are predicting the click, and then using that information, you're gonna put a new ad in the website. So that's a very good example. Any other? Okay, so can you expand on that? Oh, maybe let me see if there is a mic. Is there a microphone? Thank you. So that everyone else can hear as you as well.
So face detection. Uh, uh, so we train for some small set of human faces, but after the training is done, it will recognize new faces also. So
So
it has
face
an
recognition, exactly.
face detect.
Or detection, okay,
Detects.
sure.
It will detect new faces also,
Uh-huh.
new humans which algorithm had not seen before.
So how would you detect face? Maybe a shape of nose,
So
your
there are,
eyes, your
yeah,
mouth,
the
so,
pattern.
right?
It
That's
will
data you
find the
input.
common pattern across the whole training data set.
Yeah,
And
and Binod is not here, but he's going to talk about these algorithms that are actually designed to recognize face and do face detection, and that's also an example of supervised learning. I heard some more examples there, but is there the last one someone wants to share in the back?
Facial landmarks prediction. Facial landmarks prediction.
Facial landmarks prediction. So you want to predict.
Using histogram gradient
Mm-hmm.
of foreign gradient. So facial landmarks prediction using HOG images.
So what's your outcome there?
So you'll get the coordinate of your face.
And what's the input as predictors?
It's an image, and you have to convert it into HOG parameters.
Okay, that's really good. You guys are already ahead of the lecture, not just this, but of the entire course. Thank you. So just to formally motivate supervised learning, which you guys have already talked about, there are a set of measurements, X and Y. And we call it training data because we build model using these training data to then construct a prediction when you see a new data, new predictors, X naught. And those are usually called test data or validation data. So you train on a particular data, and then you want to predict an unseen, previously unseen new data. Few important components of supervised learning. One is you know what the outcome are. You know the labels because you're teaching the model how to learn so that when you see new data, you can use that model to learn also on the new data. So there is some supervision done. X's are usually called predictors or features in machine learning. But if you're from statistical background like me, then you call it covariates. But they all mean the same thing because those are the features you're inputting and you're trying to learn your output from the features that you have. And to go back to the lecture yesterday, if you're building a probabilistic model around outcome, then you use capital letter Y as a random variable, and small letter would just be a realization of that random variable. Okay, so we'll start with the most simple. Well, it's not most simple. I guess it's the second simple supervised learning. If you wanted most simple, then you just predict mean, right? If you have outcomes, you use that mean as a prediction, and then every time you see a new data, you can say that's the new prediction. And that would be a very simple supervised learning. And then if you want to build on that, you can start using features or predictors to build a regression model. So this is a formulation of linear regression here. And the important parts, the reason why it's called linear is because the model is linear in predictors. So you can see why we can have model Y as a linear function of X and some parameters beta. So I have used K to indicate that there are 1 to P different predictors. So if I was thinking about predicting weight from age, height, and gender, then I have 3 predictors. And then here X would be for age times beta for age plus height times beta for height plus, or no, age, gender, and weight. So age, height, and gender. So weight is the outcome variable. So age, height, and gender will be in just the summation of each other. And this is a linear function, right? So that's why it's called linear regression. And usually we represent linear regression as some linear function of predictors plus noise. So things that X will explain. And then there is always some extra noise or nuances that you can't really explain. And they're called errors or noise variables. So things that are explained by X would be the signal here. And then anything that you cannot learn or that's just nuisance variable is noise. And in learning model, you want to learn signal from the data and separate signal and noise. So here I have a plot of height and weight data. So I have people with height between 50 and 70, and then this is pounds, it's not kg, but it's between 150 and 210 pounds. So if I were to build this linear regression model, then all I'm saying is height and weight have linear relationship. So somehow I need to know what this line is. And then if I see a new person who has height of 60 inches, then I will just say what the predicted value would be for that person along this line. Are there any questions for the formulation of linear regression? All right. So, okay, you know how to build a model. You've said y is a linear function of x's in some error terms. But how would you then go about predicting at a new x naught? So first, to do prediction, you have to first build a model and estimate parameters. So it's called training. You're training your model to learn what the parameters are. And once you know that, then you start building a prediction model where all you're computing is expectation given new data point. And that would just be this part here, because expectation of error term is 0. So if you had a new point with age of, or height of 60 inches, all you're doing is you're inputting 60 here, and then you know some beta hat from this objective function, and you take a product to get the expected height or expected weight at height equals 60 inches. Okay, so what I have taught you so far is, one, how to represent this model for linear regression. And then if you have a model, then you want to find the parameters. And usually you want to find a parameter that will predict the best, right? There's so many ways, different values that beta can take, but the one you want is the one that will give you the best prediction. But how do you define best prediction? So there should be some criteria to define what is good. And once you have that, then you can go about doing the prediction. So to learn beta, we'll call it estimation problem because you're estimating parameters from the data you have. The first way to think through estimation is just maximizing likelihood or minimizing the negative likelihood. So we learned yesterday that likelihood has a lot of significance. It gives you information about the probability, how likely something is, given that parameter, right? So in linear regression, we want to maximize the likelihood of beta, which means probability of y conditional on that beta. And it's similar or equivalent to minimizing the negative likelihood. So negative likelihood will be your loss function if you're talking about loss. So for the likelihood, what do we need then? I haven't talked about distribution at all, right? So if you wanted to compute likelihood of parameter, then you need to have a probability model or some distribution model. Okay, so it's common to assume that epsilon has a normal error because in linear regression, I forgot to mention a very important point. We assume this is a model built for outcomes that are continuous. So we'll have a different model for discrete data, but here I'm assuming something like height. So height is a continuous variable. Your income could be a continuous variable. Age is a continuous variable. Stock prices is continuous variable. What could be other continuous variable where you use linear regression? Sales price is linear regression. I hear voices, but I don't understand what you're saying. Can you say it loud? Huh? Where's it? Oh, wow.
No, it's temperature, pressure.
Oh, temperature and pressure. So temperature is linear regression too. So it makes sense to assume that epsilon has a normal distribution, right? Yesterday we learned that normal distribution is a distribution for continuous variable with some properties. So if we assume epsilon has normal distribution, then our data points will also have normal distribution. But the center of the distribution, which is the mean parameter, will just be x1 beta, and the variance carries over. And this is just by using the property of normal distribution. Because we said our y is a linear function of x, beta, and epsilon is the only one where we have a distribution. So if we were to look at expectation of y, then expectation of y will be x beta. And we can also compute variance of y in a similar way. And we can show that yi, conditional on the data features, and beta will also be a normal distribution. Then we know how to start thinking about likelihood, which is probability of y conditional on x and beta. And we're also assuming that each data point we see is independent. This is very key here. If they were not independent, then we can't really write this as a product. And then our likelihood becomes very complicated, and we have to resort to other methods to start computing MLE or the value of estimate of beta we want to study. But making this assumption, if we can assume yi is independent, then it just reduces to the product form, and we can start thinking about each of these individual distributions rather than joint distribution of all the y's together. And as Suresh talked about yesterday when we were taking MLE, we usually use log rather than the likelihood itself. All right, so our goal here was to estimate beta hat. We want to, and one way to think about it is to find the parameter that maximizes the likelihood or minimizes negative likelihood. And then we went about assuming epsilon as normal error. And then we can now start thinking about the likelihood of beta, which is just the PDF, joint PDF of all the y's conditional on x and beta. But because y's are independent, you can write it as a product. Then log likelihood would just be a sum. And I can even start decomposing it into two parts. There is a part here that does not have beta at all, and a part that has beta. So what, in essence, all we care about then is maximizing this part, right? Because this is just a constant in beta. All right, is this clear? Are there any questions? If not, then I'd like to work out this maximization or problem to find what beta hat would be. So I want you to get me a solution of beta, maximum likelihood estimate.
Question I didn't understand. So we basically assume that the errors are normal distributed.
Yes.
And then again we also.
So if we assume the errors are normal distribution, then the model we're working with is this linear model, right? And the expected value of error is 0. And the sum of normal is actually, this is just a constant. This has distribution. So we can show that y itself also has a normal distribution with a shifted mean. And that mean is given by this part here, because this epsilon just has a mean of 0. And you can also show that the variance of the y's are the variance of this error term, sigma square. So what we want to do now is find some beta hat that maximizes. So log of exponential would be the number itself. So we want it for all the points. Basically, she just took derivation and solved as we did earlier. यो पार्ट चाहिँ अलि माथि लेखिदिन्छ यहाँदेखि त्यो मिटे पनि हुन्छ Thank you. So let's have a round of applause for Rima. Are there any questions for this solution? If not, I'm going to discuss also the case with intercept. So I got some question where people were asking, where did you put the intercept, or why are you assuming the intercept is 0? I'm not necessarily doing that, but I just included intercept in the X matrix itself. And I'll show you why that is the case. So the linear regression that we are all familiar with is written as something like yi equals beta 0 plus beta 1 x1I plus epsilon I, right? So what I assume now is something like beta 0 is x, or yi is the product of beta 0 times 1 plus beta 1 times x1I plus epsilon I. This is just the sum of beta kx k to 2. So my x now is this long matrix with all 1. And then x1, x2, right? And if we wanted to go about solving for this term here and find the solution for each of these terms, we can either do differentiation with respect to beta 1 first and then with respect to beta 0 and then solve for it. Or we could just assume that the beta itself is a vector and then find a vector solution for it, which is right here. So is this clear that we are still assuming there is intercept in the model? So if I were to give you data with x's and y's and ask you to predict first, how would you go about doing that? So you'll write the regression form. Here we have linear regression because our outcome was continuous. We have one or two covariates. And then we'll next define the loss function or something we want to maximize or minimize. Usually loss will be minimized. Likelihood is maximized. And then you have a solution for beta. And once you have an estimate of this coefficient beta hat, which is the parameter, you can start thinking about predicting for a new variable. So you need to start with writing the model form that you're trying to learn and go from there. And that's same for any other machine learning supervised problem too. I mean, you don't have to necessarily constrain yourself to linear regression. Even in linear regression, you could start adding, x squared, x cubed, then it becomes a polynomial rather than a line. But it's still linear in the covariates. Or you could think, some other functional form that's cubic, spline, and then to get even more complicated, you start thinking about deep learning, others. But the basic idea of supervised learning is similar. You're interested in predicting this outcome, y, from set of covariates, and you need to now start thinking about how to build a model around that and some criteria that you want to maximize or minimize, because you want to get as close to truth as possible to minimize your prediction error. I think a lot of people like linear regression because it's simple, it's easy to understand, you know what you're doing. It has been done for ages also because of the computational simplicity. There is analytical solution to get beta hat. In most of the cases when your features or predictors are not really big, so you only have 2 or 3, maybe 4 predictors, then you have a global maximum solution. Also assuming your x's are independent. There is some assumption, but you can get the best solution possible. And that is a really good property that we'll like in our estimator. Then what you're getting is really good. There's also this interpretability and simplicity. Like you can think of betas as a coefficient. In the example of weight and height, so if my coefficient was beta was 2, then what you're basically saying is with a unit change in height, the changes in weight is 2 unit, right? And there are also other favorable properties of regression, linear regression, where you can show that as you get a lot of sample, you get closer and closer to truth with very high probability. And if you were to find a new method or think about model building, then this is really important property. You want to know whether you're getting close to truth or not if you want to learn the truth, or if your prediction error is going to 0 or not if you want to generalize it. And then there are so many software packages to fit this model. Like I want to see how many people have used linear regression in this class. Okay, what packages did you use? Okay, scikit-learn. Stat models. What did you use? Panda? Okay. In Python? Okay. IBM statistical tool. You don't even need to know Python, right? You could use SPSS, you could use uh, Excel, SAS, Stata. So it's a very approachable tool, and that's why it's so popular, and a lot of people like to use it. But then, I heard something. No. Then there are also cons to it, right? Because, of course, it's simple, and the real world is never that simple. Now we have this problem where we have so much data, we have more data than we can handle. Like, if you're thinking about applications in medicine using health records, there's so many data you have for each patient. You know their blood pressure, you know their, I don't know, heart rate, vitals, what the sodium level was, what the potassium level was, what the magnesium level was, what their height was yesterday, what their height was the day before, and MRI, CT scans. So the dimension of data just increases so fast than the number of observation you might have. And in that case, a lot of assumptions we're making about linear regression might not be sufficient, or it's too complicated that we can't even fit it because the solution doesn't exist. So that's why a lot of new machine learning methods have been developed to overcome some of the deficiencies that linear regression has. Even though it's simple, once the scale of your problem becomes larger, and you need to have like more complicated model to account for the complicated relationship between the features you have and the outcome you have, then you have to expand beyond what we just learned about. All right, are there any questions? We won't be talking about a lot of complex model today, but just to give you an idea of what to look forward to in the rest of this week, we're expanding on the simple model and try to address some of the issues that they have to account for that. All right, so if there are no questions about linear regression, then I'm going to proceed towards classification problem. So for linear regression, we just talked about continuous data when our y's are in a continuous format. But what if we just want to classify? Like we want to know whether the weather tomorrow is going to be rain or sunny. So we only have two options, and that's rain or sunny. And we want to label our data when we get a new information to those two classes. So rain is a one class, sun is one class. Or in medical data, after a major surgery, the major risk is that the patient is going to die. And we don't want them to die, we don't want them to survive. So it will be useful to know using the prediction model whether the patient is going to be alive in the next 15 days. If the patient is at risk, our model predicts that they're more likely to not survive, then we want to intervene and make sure that we provide the care they need so that they will survive. So this is like very useful example where prediction model can be used in the important setting. And again, for when a patient comes to surgery, we have all this information because we are required to monitor them, take their health information, past records, and we have learned from past, like we also have data which patients did not survive, which survived. So that when a new person comes and we want to use their features, we can use that to predict how likely they're going to be survive or die. And those two are now my classes or labels. And we want to classify into those two classes. The other example would be hypertension, again from medical data. We have this whole historical data where we classify patient into two groups, high risk of hypertension, low risk of hypertension. And then maybe we say it's related to age, so age is a good predictor. Yes, and I'm only using hypertension as yes or no. There could be various ranges, but I'm ignoring that fact. So because we want to classify patient into high risk and low, so yes, hypertension, no hypertension, let's assume that. People get older, they're more likely to get hypertension, and there will be in the class hypertension. Then when I have new patients who are older, maybe I can predict that, they are more likely to be in that class, and then I can treat them accordingly. So basically in classification, our goal is to, again, to find a rule which will help us to classify new subjects into different classes. And we'll learn that using existing data where we also already have labels for those outcomes. So this is a key difference from the other set of problems that we'll talk about later, which is clustering, where we don't have labels, but in classification and also in regression, we already know for some patients, when we have their features, we also know what their outcome looks like. And that helps us to learn for new people or new observations. Okay, so this is what I already talked about, but in a graphical format. An example of data we might get. We have patients who have hypertension. We have patients who don't have hypertension. So yes will be 1, no will be 0. And along x-axis, I have age. You can already see, like, for yes, the ages are usually on the higher range. And for no's, they're on the lower range. So if you want to build a classifying model so that when I see a new patient at age 60 and I want to know their risk of hypertension, whether they're more likely to be yes or no, I need to have a rule, right? And a simple rule could just be here, where I say if you're 45 years old, you're going to be you're going to be yes reason, and if you're less than 45, you're going to be on the no reason. But then if using this rule, there are a lot of yes patients who have been misclassified. And we don't want that, because then that's not a good predict model. What we want is to minimize as much as we can this misclassification. So the number of patients that are wrongly classified into wrong label. We want to be correct as much as possible. And if we said, okay, for 60 years old, if you're older than 60, you're more likely to be hypertension. If you're less than 60, you're no in hypertension. Then we're even making more mistake, and this is really bad. So someone who gives you this rule and goes by it, they're just misclassifying all the patients less than 60-year-old as no, and that could increase their risk of hypertension. You're not going to treat for them. No, so it's a bad classifier. We want a good one. One of the earliest models now built for classification is a logistic regression. In logistic regression, we're still following this functional from where outcome is related to the feature or covariate. But because our outcome is yes and no, or 1 and 0, we can treat it as linear regression, right? Then our prediction model will fail quite a lot, because you're assuming that the range of data is from minus infinity to infinity, when in fact it's only 0 and 1. So to account for that, you will instead model one probabilities, and we'll model it such that this log of odds ratio, so probability of 1 versus 0, is a linear function of covariates. What that means is now we're fitting this sigmoid function, which represents probability of being in class 1 for each of the patient. And using that, we can start building prediction for each of new patients. So as an example here, I first represent what the model is going to look like. And the intuition here is to account for the fact that there are only two possible values for our outcome, 0 and 1. So I'm working with classification for 2 labels. There could be multi-class, but we'll ignore that for a while. We'll model it as a ratio of probabilities, because if we know probabilities, then we can probably assign them to which class they're more likely to be in. And then we also linearized it by using the log. And log of probability will have this same properties as outcome variable. All right. So we'll take some time for tea break. We'll come back, and then I'll start from this slide again. And we'll discuss some more properties of logistic regression. Continue. If you have questions, you can ask Surya later or one of the organizers. Okay. So let's go back to our motivation for classification. So just to recap what we learned this morning. So we learned one of the methods to do supervised learning. We learned linear regression. And there, the outcome was a continuous variable. And we model it as outcome as a linear function of predictors. And we saw how to estimate parameters so that we can predict for a new observation. And then we saw that we can either estimate using likelihood-based method or using some loss criteria where we want to minimize prediction loss. And that idea will carry over throughout the supervised learning method, and other machine learning methods we'll later learn. So to move from continuous outcome, we're now going towards classification, where the outcome are ordinal or labeled or classes. So there are different terms that are interchangeably used. Usually when we say discrete outcome or categorical, then there are different categories. I will only focus on 2 categories, so yes or no, survive or did not survive, red or blue, sunny or rainy. But then, it can also be multiple classes when there is red, blue, and white, or sunny, rainy, and cloudy. And these methods will just extend to those problems as well. It just gets a little bit more complicated. All right, so in this example, so we're working with this example here where we want to predict whether a person is going to have hypertension or not as a function of age. So if I knew your age, can I predict you'll have high hypertension or not? And this is the data I have where I observed age, and then I plotted yes and no, yes as 1, y as 0 as no, no as 0. And then we saw people with older age are mostly yeses, and then patients on the lower age, younger ones, are mostly on no. So your risk of hypertension seems to increase as you age. And if I see a new patient here at age 60 now, can I predict with good accuracy? So can I predict where my prediction is very correct to say how likely this person was going to be either of these classes? And then we also talked about this on building prediction rule. So the rule is to classify. We want to find this certain threshold here as a function of age. So this threshold where we can say, okay, if you're older than 50, you're in the yes class. If you're younger than 50, you're in the no class. Or maybe if you're older than 60, you're in the yes class. If you're younger than 60, then you're in the no class. There are so many rules you can have, right? You have patients from 20 to 80, so every point could be your prediction threshold. And some thresholds are better than others because at the end of this, we want to formulate a criteria where we're not mislabeling these patients. Criteria where each of these points will be correctly classified to the colors they have. And that is the goal of classification. And then when we see a new person, we also want to classify them into the classes with very high accuracy. So accuracy is the word I'm going to use a lot when I talk about classification. And it's similar to the idea of loss or square error loss in regression. In regression, I wanted to minimize the difference between y and predicted y. Whereas in classification, I can think of it as the number of these points that are correctly classified. I want to maximize that, or I want to minimize the misclassification. So one way to think through it is to go back to the formulation that we already know, regression. So we talked about outcome being a function of covariates or features, and we want to model that. And in regression, our outcome was continuous variable, and then we modeled it using linear regression where y equals x beta. But here now our outcome are categories, and if I use 1 and 0, there are only 2 possible values. So I don't want to use linear regression because then I'm allowing for the outcome to actually go beyond 0 and 1. And if I'm predicting, I don't want that, right? So instead, I would model the probabilities rather than the outcome itself. And I'm modeling probability of being in each of the classes. So in class 1 versus class 0. And the sigmoid function here now is the shape of the probability function. And that's what we're modeling. But if I take this log transformation, then I have a linear relationship. So basically, it's linear as well in x's. So we see some similarity between linear regression that we learned earlier and logistic regression. Here, the motivation being wanting to model probability of being in each classes. Okay, so if I can get this line from my model using my data of hypertension and age, and if then when I get a new patient at some age, I can see where they fall in the line, then I can know the probability of being in this class 1. Then I can start thinking about classifying them. I'll build some role based on the probability, maybe higher probability. I can say, okay, you're in 1. If it's low, I'll say you're in class 0. So is that clear? So this is like a very systematic way to think about classification when we are in regression framework. So just to give this idea of prediction, what we now have is a prediction probability based on this model. Here I have log of odds ratio as x beta. So if I were interested in writing p of y equals 1, then that will be a function of some transformation of x beta. And what I would like you to work on now is actually find the value of probability y equals 1 rather than this log form. Can you work it out? Even the answer is already here, so we should be getting something of this form when I work this formula to get only the probability on left-hand side. So what I wrote there can be rewritten as this, right? Because probability y equals 0 is just 1 minus probability y equals 1. And now I want you to work this out so that the answer we have is PR y equals 1 equals something here. So the first step would just be to take exponential in both sides. Because we just learned that exponential of the log is just a number itself. I will talk about it later. It is an operator. It's called indicator function. But yeah, thank you for asking. So I'll go into some detail about that. But before even going there, I want you to start thinking about writing probability. You done? No. You done? So I want someone from this side of the room to come and work it out if you've already worked on the answer. You can use that. All right, very good. What's your name? Okay, let's have a round of applause for Irina. And can you all see this? So the first important step that she took here was to exponentiate both sides. So when you do exponentiation of log, you just get this term here plus e to the power x beta. And then basically you're solving for probability y equals 1. Is that clear? So the answer she gave us now is okay, can you all see this? So what does this mean? If we can find a way to estimate this parameter beta from our training data, then for a new set of covariates for your new patient or new observation, we can start thinking about probability. I'll call it p hat because we're estimating it, but y equals to 1 for that new person x0 just becomes y plus 1 plus e to the power x0 beta hat, where beta hat is something we estimated from this functional form using the training data. And now we can use this form to get predicted probability of being in class 1 given this feature for this person using this formula. Right? So this is what it means by predicted probability. You're computing probability in being some class for each of these new observations. And one more thing, if you know probability of being in class 1, then can you also compute probability of being in class 0? 1 minus, exactly. So I also have probability of y being in class 0 given x0 here. So with these two probabilities, now I can think about forming a classifier. That's what they call when you're building a rule to classify. And I gave you an example of a rule here where I'm saying, okay, this new person with this feature x0 will be classified as 1 if this predicted probability is greater than 0.5. And if it's less than 0.5, I'm going to classify less than or equal to 0.5, I'm going to classify it as 0. So this I here, someone asked me about this operator. And I'm using I of some x equals 1 if x is greater than, let's see, this I is an indicator function. If I say something like that, then I'm saying, okay, if this condition is satisfied, then give this I a value of 1. If it's not satisfied, make it 0. And this is also known, I think they call it Boolean. Is indicator function also called Boolean? It's okay. But I call it indicator function, but there are also many other names too.
Yeah, I think it's called indicator.
Yeah. So exactly. So how can we find this value here? I just said 0.5, but why does it make sense? Can there be other threshold where we can start classifying patients into different classes or new observations? How do we build this rule? And when a lot of people talk about building a classifier, right? And the whole idea of classifier is to build a rule that will allow us to classify different observations into different classes. If there are only 2 classes, then we can think of it as like 1 and 0, and we want to build a rule where we're saying, okay, if the predicted probability is, above certain threshold, it will be classified as 1. If it's below certain threshold, it will be 0. And then we also have to start thinking about how it translates to the feature matrix or covariates. Okay, so this is a little dense, and I'll start walking through it because I don't know if you guys have heard, but linear logistic regression is also called linear classifiers. And there are other classifiers that could also be linear. So what does it mean to be a linear classifier? Okay, so we'll just think through it for some minute here. So a convenient property of this form of logistic regression is that now when we start thinking about classification, it just translates into a simple linear form. Linear in the covariates when you're building classifying rule. And as I mentioned earlier, if I am to classify a value, y, we want to assign it, so by classification, what does it mean to classify? We have, discrete choices of outcome, and we want to put each of the observation into these classes of outcome. So initially, we want to assign the value k to the outcome such that probability of being in that outcome is maximized for all of these classes. If I'm thinking about it in terms of 0 and 1, so I have two classes, what I'm saying is for a given x, I want to find a classifier such that probability of y equals 1 conditional on x0 is maximized. This conditional probability for the feature will be maximum. So in two classes, what does that mean? Which means this probability has to be greater than the probability that y equals 0 given x0. Right? So I will only assign a new observation to class 1 only if this predicted probability for that given value of feature is bigger than or greater than the probability of being in another class for the same value of feature or covariate. Okay, so what I want you to now do is this still working? Yeah. To go from step 1 to step 2, where I have now moved from probabilistic statement to this another statement that only involves x and beta. And we also have a formula for probability here. So is my question clear? Not clear? Okay, so can you see this first line here? Was that clear, what I'm trying to do? Okay, and then I'm saying, okay, from first line to second line, I have some equivalent expression. I'm saying this inequality in probability is equivalent to having this inequality, the second line. And I'm asking you to show me this. And just recall that we have expression for both of these probabilities using our logistic regression model.